Today's lesson is going to be basically a math lesson. It's about the universal wave equation. So it's a standard equation that applies to all waves and waveforms. It's a nice, simple little equation. You shouldn't have too much troubles with it mathematically. I am going to point out if you hear a little bit of background noise, I have a 3D printer going on in the background. Those things take quite a few hours to print most things. So just try to ignore it as best you can, and hopefully the microphone isn't picking it up. So good place to get notes for this if you just want to print them off yourself is on April 2nd on the calendar. And again, there is a nice reference textbook in the Unit 3 Waves and Sound reference, but I linked it inside the April 2nd little drop down. And so that would just be the universal wave equation, chapter 6, section 3. So let's just get going with this. So the universal wave equation is a really simple equation that relates the speed or velocity of a wave as it travels through space to be a product of the wave's wavelength as well as its frequency. So if you know the wave's wavelength, if you know its frequency, you can calculate the speed, or if you know the speed and the wavelength, you can work that equation backwards and solve for the frequency. And likewise, if you know the frequency and the speed, you can work that equation backwards to solve for the wavelength. So again, wavelength is this fancy little Greek letter called lambda. It looks mostly like an upside down Y. And this is just a cute little equation to get you through pretty much the rest of the school year, because we're going to talk about waves and waveforms with respect to just mechanical waves as well as electromagnetic waves when we start getting into the light subject. So this little equation applies for everything. Occasionally, I might use velocity to call V, because that is what it's supposed to represent, but we're not going to talk about going in different directions. We're going to just basically talk about a wave moving forward. So technically it would be velocity, and therefore you'd have to consider forwards, backwards, left, right, north, south, east, west, and everything in between. So I'm going to interchange speed with velocity once in a while, just out of habit, due to kinematics. So typically I see V, I think velocity, but speed is technically I'm going to have the unit V, sorry, the symbol V. Frequency is a bit simpler, lowercase f, and then wavelength again is just lambda. So you'll just have to kind of recognize those symbols when you guys do your math. Speed will typically measure in meters per second, occasionally centimeters per second, once in a while millimeters per second. If you ever get kilometers per hour, it's probably a good idea to convert it into meters per second, because we're going to be measuring our wavelengths typically using meters, and then we're going to have to get into prefixes: centimeters, millimeters, micrometers, nanometers, occasionally kilometers. But after that, if you have larger wavelengths, then you're probably going to be using scientific notation. Likewise, if you have smaller wavelengths, you'll be using scientific notation. So just go over your metric prefix form that you got in the chemistry unit. When it comes to frequency, your basic unit of frequency is the hertz, which again is a per second. Frequencies are typically going to be larger values when it comes to most waves. So it's not uncommon to see, starting from the lowest here, kilohertz, which is 1,000 hertz, megahertz, which is 1,000,000 hertz, gigahertz, which is 1,000,000,000 hertz, and then terahertz, which is 1,000,000,000,000 hertz. They can go higher, but for the most part, you won't really see them. You might be familiar with gigahertz and terahertz, megahertz, or in the sense gigabytes, terabytes, megabytes. So you've probably heard those prefixes before used on your computer. So hopefully they're not new words for you. So there's not much more to go into than that. So let's just get into some math. I've got 3 math problems to do with you. So example number 1, a wave has a frequency of 5 times 10 to the negative 1 hertz. So that means you're getting half a wave made every second, and a speed of 3.3 times 10 to the negative 1 meters per second, or 33 centimeters per second, if you'd rather write that down. What is the wavelength of the wave? So typically when you have to read a problem, try to identify all the variables. So frequency would be your 0.5 hertz if you want to ignore scientific notation. Speed is going to be 0.33 meters per second, again, if you want to ignore scientific notation. and we're looking for the wavelength. So just typically identify what's given to you and then just work out the equation. Now we're looking for the wavelength. The way this equation is written, that's not really what we want. So we have to manipulate the equation. First thing we need to do is get the wavelength by itself. In order to do that, we have to divide by the frequency. So if you divide by the frequency, both sides, so what you do to one side, you have to do the other. Your frequency cancels out and you're left over with an equation for wavelength to be your speed divided by your frequency. So once you get that far, it's just a matter of punching in your numbers. So again, I ignored scientific notation. I just converted 10 to the negative 1. So I moved my decimal place to the left once. So that's 0.33 meters per second. Likewise for my frequency, I just moved the decimal place to the left once because it's negative 1 and I've got 0.5 hertz. So the way it looks, a meter, a per second, and a hertz, all these units are different, so nothing cancels out. So you kind of need to remember that a hertz is the same as a per second. So if you can recognize that, you can see that actually a per second in the numerator should cancel out a hertz in the denominator, because then you have a per second up top and a per second down below. When you get a per denominator and a denominator, that thing should just go to the top, or just try to remember that if you take a per second divided by a hertz, they will cancel out. And you should just be left with meters. So 0.33 divided by 0.5 is the equivalent of multiplying it by 2. So your wavelength would be about 66 centimeters in length. So about 2/3 of a meter, if you will. Second example is going to be a light example. So here we have a red laser light, and it's traveling at a speed of 3 × 10⁸ meters per second through space. It has a known wavelength of 750 nanometers. What is the frequency of the light? So light, if it's traveling through space and through air, for the most part, it's going to have a set constant speed. And that speed is 3 × 10⁸ meters per second, or 2.9979 or something like that, times 10⁸. But rounded up to 3 significant figures, we just call it 3 × 10⁸. This is a constant for the most part. For any time you're dealing with light. We'll get into that in more detail in another lesson, but if you're doing some problems, if there's any other problems that are involving any kind of light, you can just remember that number and maybe your math will be a little bit easier. So, like all problems, point out what's given to you. You've got a speed, so we know because it's got meters per second, so our speed is identified. We're given a wavelength, so that's 750 nanometers, and we're looking for a frequency. So I'll just put frequency off to the side. That's what I'm looking for. Now, mathematically, when you guys are working with metric prefixes, I need you to recognize when you see a metric prefix like nano here, look at your chart, and nano means times 10 to the negative 9. That's how I want you to see a nano. Don't just plug in 750 into your calculator. You have to recognize that that's 750 times 10 to the negative 9. That's what nano means. So this is what you should be entering into your calculator. Now, this is not proper form of scientific notation. So recognize that. If you go, okay, well, I have to have it in proper form, then that means technically you should move your decimal place once, twice to the left. So we should have moved it twice to the left. And if you move it to the left, we have to count up. And technically it'd be 7.50 times 10 to the negative 7. So this is what it is in proper form. Typically, I'm lazy in my own calculations. So if I'm doing my own calculations, I just ignore the proper form and I would literally plug this into my calculator, because I don't have to remember if I have to move the decimal place to the left or to the right to get it in proper form. A lot of the times, grade 11 students will make that mistake. And you might call it, you might move the decimal place 2 to the right rather than 2 to the left when you're trying to put it in proper form. So just leave the number as is. If you're getting your final answer and you had to use scientific notation, I expect your final answer to be in proper form. But if we're just going to be working mathematically with a number, you can leave it out of proper form as you move forward. So I'm going to leave it out of proper form while I do my math. So we're going to look for frequency, identify your universal wave equations. So kind of like the last question where we were looking for wavelength, we had to get wavelength by itself. So we need to get frequency by itself. So divide both sides now by your wavelength. So cancel that off. And you have a new equation for frequency. So frequency is your speed divided by your wavelength. If Once you get that far, again, it's just like plugging in numbers. Your meters, meters per second on the top divided by meters down below, your units should cancel out properly, because a frequency does have the units of a per second. So if my meters cancel out, that'll work out for me. I do have a per second left, and I know a per second should be a hertz. Numerically, you guys can punch this through your calculator, so I'm not too concerned about that numerically, but do make sure that when you're calculating frequency that you will end up with a per second in the end. And if you do have a per second in the end, you can just convert that to a hertz, right? Because they are an equivalent unit. Hertz is the proper unit. Don't leave it as a per second. Leave it as a hertz. Last little thing to point out with this number, so you got 4.00, decimal, 4.00 times 10 to the 14 is what your calculator will probably say. Recognize that that is correct, but I want you to recognize that often you might see this number represented differently in future problems. So when I see 10 to the 14 hertz, I recognize that a terahertz, so the metric prefix for tera would be times 10 to the 12. So if I have a terahertz, that's times 10 to the 12 hertz. I definitely have times 10 to the 12 hertz because 14 is a bigger number. So if I consider 10 to the 14 hertz as take out 10 to the 12, so if I take out 12 from that 14, I'll be left with 10 to the 2, and I can replace that 10 to the 12 with a tera. 10 to the 2 means 100, so I can change this 4.00 times 10 to the 14 hertz into just 400 terahertz. No decimal there. And that's often how you'll see a lot of frequencies represented with metric prefixes. But if you left it at 4 times 10 to the 14 hertz, that's also correct. I'm just kind of giving you some variance to your answers and just what you might be expected to see in your future. So expect to see terahertz. Last question is a sound question. So sound waves, they're longitudinal waves. The last two questions, I'm going to assume that they were transverse waves. Well, light is a transverse wave. Sound is a longitudinal wave, but that doesn't matter because it follows the universal wave equation just the same. The universal wave equation is universal. It's for every type of wave. So if you have a sound wave that travels towards an observer at about 354.6 meters per second, it would have a wavelength of 2.65 meters. So what is the period of the wave? So this one's a little bit different. Frequency is not involved. So recognizing what's given, we were given a speed, 354.6 meters per second. You were given a wavelength, 2.65 meters, but now we're looking for the period. So the universal wave equation does not have period in it. Universal wave equation has speed, wavelength, and frequency. So you're going to have to remember a previous lesson. So there's the universal wave equation. Previous lesson where we talked about how frequency is the number of cycles divided by your time, number of cycles per second, and your period is the time it takes to make one cycle. So that means they're reciprocals of each other. Frequency is the reciprocal of your period, and period is the reciprocal of your frequency. So if you can remember that, you can just substitute in for frequency in the universal wave equation 1 over the period. And if you do that, you do replace that frequency with 1 over t. Lambda times 1 is just lambda, and you end up with a slightly modified version of your universal wave equation, where it is now associated, the speed is equal to your wavelength divided by your period. So if you think of the units, wavelength would be measured in meters. Your period is measured in seconds. You end up with a meter per second. So that works out. When in doubt, try to make sure you can think about your units, whether or not your units are going to work out in the end. That's half the problem with physics. If your units don't work out, you've done something wrong. Okay, so we're looking for period. Period's not by itself. Period's in the denominator, so that means we're going to want to switch it out with our speed. So typically, I would just switch the number on the left of the equals with the denominator on the right. Technically, mathematically, you're multiplying both sides by your period to get the period out of the denominator. And then since you want period by itself on the left, you have to divide both sides by its speed. So you're technically just doing a little bit of cross multiplication just to get period all by itself. So period is equal to your wavelength divided by your speed. Once you can get that equation written out, it's just again a matter of writing out your numbers and doing the math. So I still have a meter divided by a meter. That's good. That's what I want in the end, because there's no measurement of length in your period. So those will cancel out. And then I end up with a per second in my denominators. That means I have a denominator within a denominator. When you have a nested denominator like that, you can just bring it up to the top and it becomes a numerator. And that's just a product of fraction multiplication. So that becomes a numerator, and you end up doing a quick division, and you end up with 0.00747 seconds. And you can write it down in scientific notation, 7.47 times 10 to the negative 3 seconds, or you can replace that 10 to the negative 3 with a metric prefix, just say it's 7.47 milliseconds. I'm using 3 significant figures because my wavelength was just written in 3 significant figures, so that's where I'll stop it. So those are just 3 examples of ways of manipulating your universal wave equation. Period will sometimes come into the mix, so do remember you can replace frequency with period if you remember that reciprocal relationship. And hopefully the 13 questions shouldn't be overly too difficult. So I'll stop here.